All right. In this screen recording, we are going to look at the situation where we have one-dimensional motion in a special case, and this is going to be very useful to us. A special case where acceleration is constant. So if we have a constant acceleration, if we look at a velocity time graph, that means the slope is constant. Since the slope of the velocity time graph is equal to acceleration, then the acceleration is going to have a constant, it's going to have a slope of 0 because the velocity increases at a constant rate, which means the acceleration is constant, so the rate of acceleration never changes. And that means that the instantaneous acceleration at any point is going to equal the average acceleration for the entire time interval. There's no difference between an instantaneous and an average acceleration if the acceleration is always constant. And since my definition of acceleration is change in velocity over time elapsed, I can rewrite this instead of v final minus v initial. Sometimes they like to write it as v minus v0 over t instead of using the time, the elapsed time. We just collapse to t a lot of the time, and we like to just shorthand it v minus v0. But if you do that, you can then write that the velocity is the initial velocity plus the acceleration times time when the acceleration is constant. And if you look at the graph here, that's the equation of this line right here. V, this is the y-axis, equals v0, which is the y-intercept, plus acceleration times time. So if I start with a velocity v0, and then I accelerate for a time t, my final velocity is v0 plus the additional velocity I gained by accelerating at that rate for time t. So my final velocity is the initial velocity plus the acceleration times the time. So an example would be, let's say I started with a rate of positive 2 meters per second. I accelerate for 2 seconds at a rate of 6.0 meters per second squared. And if I do that, pretty straightforward. My initial velocity is 2 meters per second. I increase 6 meters per second every second for 2 seconds. So I end up at a rate of 14 meters per second. Okay? So that relation v equals v0 plus at is really useful, because what we're going to do is we're going to develop a system of 4 equations, not a system, but 4 different equations that relate all the kinematic variables, displacement variables, velocity, time, and acceleration, so you can predict based on initial conditions what an object will be doing at some later time, how fast it'll be going, where it is, stuff like that. And we'll do an example at the end of this little screencast. Okay? Now, if my acceleration is constant, and this is only true for constant acceleration, then my average velocity between an initial and a final velocity is just the initial plus the final velocity, initial plus final divided by 2. It's the average of the values of the velocity. And it's only true for a constant acceleration, because when the acceleration is constant, you spend an equal amount of time at each discrete instantaneous velocity, and therefore the average between the two velocities is just going to be the midpoint between the two. Only true for constant acceleration, but if that is true, then we can also make an equation for displacement. Since I know that average velocity is displacement divided by time, displacement is the average velocity times the time. In this case, the average velocity we know for a constant acceleration is just v0 plus v divided by 2. So here's a second useful equation that describes displacement in terms of initial final velocity and time. Now we're going to do a little bit of algebra and develop a few more relations that we can use. Okay? So, again, summarizing, for constant a, this and this equation are the same thing. This is just another way to write it. Now, since I already know that v equals v0 plus at, and delta x equals equals v average times t, I can substitute and get a different combination of variables and develop another equation. Now I'm developing these different equations because each one has a different combination of variables. And depending on what you know, you just want to use one that's more convenient, that has the variables that you know and the one you're looking for rather than one that doesn't. So I can get another relation by substituting v0 plus at in for v. I'm going to pop that in there, and then I'm going to do the algebra. So I replace v with v0 plus at. So the v is now v0 plus at. And I multiply it out, and I get displacement is VOT plus 1/2 AT squared. So you can see I now have an equation that has a different combination of variables. In this one, I have a displacement in terms of an initial velocity, time, and acceleration. Compared to this one, the displacement in terms of an initial and a final velocity and a time. So they're just two different, describing the exact same type of motion. They're just two different ways of, different combinations of variables. So here's an example. This is a graph that sort of represents this, that does represent the situation. So I've got a position time graph. Constant acceleration is going to look like a parabolic looking graph. The slope keeps increasing because the velocity keeps increasing. The slope of the graph represents the instantaneous velocity at, well, the tangent line at a given point represents the instantaneous velocity at the point where I draw the tangent line. If I were to draw a line connecting 2 points, that would be the average velocity between those 2 points. So this graph is representing this equation. And this graph is representing this. But what you can see is as we've discussed, we know that the area under the velocity time graph is equal, or the area between the graph and the x-axis. So if it was in the negative direction, you go from the negative side up to the x-axis. But the area underneath the graph is the displacement. And you can actually see that here because this area right here is just v times t. That's the area of this rectangle, v times t. So that's part of the area underneath the graph. So delta x for just this part of the, well, the area under this part of the graph is VOT. And then I add the area here, which is AT equals, wait a minute, what is that, 1/2? Yeah, it's 1/2 AT squared. Yeah, AT times t is AT squared, but it's only a triangle, so it's 1/2 AT squared. So when you add this area to this area, you actually get this equation, which we just derived algebraically, and it also shows and reiterates that the area under the VT graph represents the displacement during that motion, which is kind of cool. Okay? Yes, the area under the graph equal to displacement. And that's true of any shape VT graph. Even if the acceleration isn't constant, the area under it will represent the displacement during that time interval. Okay? Now we're going to do one more substitution. If we take v equals v0 plus at, we can rearrange it and solve it for t to get this term right here. And what I'm going to do then is going to take that same average delta x equals v average times t, but instead of replacing the v like we did in the previous derivation, we're going to replace the t right here with v minus v0 over a. And so if I do that, I put this in for t, and if I solve, I get another equation that has displacement in it, but this time it's in terms of initial final velocity and acceleration. So it's just another term I can use. I now have 4 different equations I can use to determine or predict the motion of an object given some initial conditions. And it can also, sometimes we rewrite it like that, same equation. Okay? And again, all these, we call them kinematic equations, are for the case of constant acceleration. So here are, in here this table there are 3, but you can also write delta x equals v average times 2t. That's also useful. Okay? So each one of these gives you different information. And each one can be used depending on, again, what you know and what you're looking for. So that's what we've derived. Now, what we're going to do in a minute is do one quick example problem. We'll do a lot of examples together, but the strategy is going to be the same. I want you guys to be as systematic as possible. A lot of you guys are going to end up, especially the easy ones, you're going to want to do these in your head or just scribble out numbers, but you really want to be really methodical because that's going to help you in the long run. So obviously you're going to read the problem and understand what they're asking. Drawing a diagram is really useful, and it's going to get even more useful as we get into when we talk about Newton's laws and forces and stuff. You know, label your quantities, and then you're going to, I like to when you label your quantities, I like to say, write down what you know, label the quantity, and write down the quantity. And then I like to write, what are you looking for? Put a little question mark next to that. Then, before you do any calculation, you're going to choose one of the equations that you're going to use to solve it, and you're going to write that equation in variables. Do not just pop in a bunch of numbers. You're going to see why this is true as we go on, and some of you are going to be tempted to do it. But just write it out without putting the numbers in, then solve with the numerical values. Okay? I really want you to follow that procedure as much as possible and be as methodical as possible. We'll all be glad that you did. All right. Now, an example of a constant acceleration is acceleration due to gravity or free fall. And this is the Leaning Tower of Pisa because it's trying to remind us of Galileo's experiment when he dropped two different objects of different masses, and they accelerated at the same rate. There was a demonstration one of the Apollo missions did on the moon. They took a hammer. I think that's a hammer there. Can't really see it very well, and a feather. I can definitely see the feather. And this is on the moon. Drop the hammer and the feather together to show that they will accelerate at the same rate on the moon due to the free fall acceleration rate on the moon. And because there's no air resistance, the feather acceleration rate is just the same as the hammer. On Earth, the free fall is not always the same if there's a significant amount of air resistance to affect the motion. If we could evacuate the air, feathers and hammers and rocks would all fall at the same rate. And we'll talk about why that is later. But we are going to use an approximation with objects that they're not falling far enough for air resistance to be a big factor, and that they're dense enough so that we're not going to worry about air friction like we would with a feather. So we're going to look at a freely falling object on Earth that's moving freely under the influence of gravity alone. And on Earth, that free fall acceleration is 9.80 meter per second squared directly downwards towards the Earth. And that's the approximation we're going to make. We're going to normally, not always, but at first, ignore any kind of air friction that reduces that gravitational acceleration. And so the kinematics equations are exactly the same, but if we're going to use positive 9.8 for g, that the acceleration is going to be, if I call down negative, we can replace that with a negative sign. Sometimes this is written as plus at, and then for g, you just put in negative 9.8. So in this, the way it's written here, you just use a positive value for g because the negative sign, the direction of the acceleration, is accounted for in the equation here. Either way, you can do it plus at and put in negative 9.8 for g, or you can just put the negative sign in here and put a positive value in for g. I mean, sometimes they'll write g equals negative 9.8 meter per second squared or 9.8 meter per second squared towards or downward towards the Earth. Okay? As usual, you're going to answer some questions, and I want you to jot down the answers to these questions, and then we will discuss them when we're back in class, just to see that we're all Feeling pretty comfortable with that after going through this presentation. So you're going to answer a question about a tennis ball as it is thrown upward through the air, about its acceleration, speed, velocity. And this is an interesting question about two skydivers jumping out, and they jump out at different times. I want you to think about this one. And same with some more question with the skydivers. Okay? Really quick example with constant acceleration. Car starts from rest. Accelerates at a rate of 4.5 meters per second squared for 4 seconds. It then moves at a constant velocity for another 10 seconds. And we're just going to determine this displacement and distance, since it's moving in one dimension, over 14 seconds of motion. Okay? Now, this is important. I have two different segments of motion, and I've got to treat those two different segments of motion separately, because these constant acceleration equations that we just derived apply to a specific constant acceleration. If there's a change in the motion at any time, I got to treat that segment differently than the first segment, and then add them together. Okay? So quite simply, the displacement for the first part of the motion, what I have is, and again, I actually tried to fit this on one slide, so I didn't actually do the full procedure. I did most of it, so I don't have a picture here, and I didn't write out what I know and what I'm looking for, but when we go over some examples in class, we will do that. So for part one, though, I know my initial velocity, I know my acceleration, and I know the time for that part of the motion. So based on that, I would choose this equation right here, because here's my unknown, and these are my knowns. So all I got to do is plug in the values. I have an initial velocity of 0, so this term goes to 0. And my acceleration rate, my time of that which I accelerate at that rate. So during that time interval, I am going to go 36 meters. Now for the next segment of motion, I'm traveling at a constant velocity. So my displacement is just going to be my average velocity times my time. But I need that average velocity, so I still need to look at part one to get that average velocity. And I know that the average velocity for part two, or the constant velocity for part two, is going to be the final velocity for part one, because I speed up, I stop accelerating, and I continue to move at that final velocity. So now I know I'm looking for my final velocity, I know the acceleration and the time at which I accelerate, and I know my initial velocity. So I know that my final velocity after that 4 seconds of motion is my acceleration rate times my time plus my initial velocity of 0. So I'm now moving at 18 meters per second. Therefore, for part two, my displacement is going to be my average velocity times my time, 18 meters per second for 10 seconds of motion, 180 meters for the second part, and therefore my total displacement is 216 meters per second. As an exercise, you guys might want to make a graph, position time, velocity time, and acceleration time graph of this motion, and that would, in another way, visually illustrate the motion of the object in addition to quantitatively illustrating it mathematically with these equations. Alrighty, that's an introduction to motion with constant acceleration and how you can calculate and predict what an object will be doing knowing its initial conditions, and you'll have a lot of the homework will involve doing these type of, analyses of different types of problems with constant accelerated motion. All right, see you soon.